Before we discuss the different inferential statistics tools, we will first discuss in Module 3 the foundations of inferential statistics, or reasons why it's possible to make generalizations for a bigger population even if the data is only coming from a sample. And the first part of the foundations is the normal probability distribution, which was covered in elementary probability theory. So again, as a review, a variable as discussed, as defined in Module 1, is anything that describes an element. So anything that describes an element is considered as a variable, and examples we've covered before include demographic variables like age, socioeconomic standing, and gender. Now, in inferential statistics, for the foundations of inferential statistics, we are talking about a specific kind of variable, which is a random variable. And a random variable is a variable that assumes numerical values that are determined by the outcome of an experiment. And the definition of the experiment in statistics is that this is an activity whose outcome is uncertain. That's why it's called a random variable, because the value will depend on the outcome of an experiment whose outcomes are uncertain. So for the variables that we discussed in the past, like again, age and gender, these are not really considered as random variables because the values are not dependent on the outcome of an experiment. And experiments are usually done by randomly selecting from a list of possible options. Like when you randomly select a person from a list that makes that activity an experiment, or rolling a fair die, or randomly selecting a card in a standard deck. So by randomly selecting, we are able to make the activity an experiment. Therefore, the outcome of that experiment is considered as a random variable. And random variables can be either discrete or continuous. So a discrete random variable is a random variable whose possible values are determined through counting, which means that the possible values are finite. We can list down and we can identify all possible values. And usually the values, since they are finite, they are usually in the form of integers or whole numbers. Examples include the number of absences in an entire semester of a randomly selected student of Ateneo, or the number of arrivals of cars in gate 2 of the Loyola Heights campus in a randomly selected interval of 1 hour. So both are considered discrete random variables. First, because the values are determined through an activity with an uncertain outcome. And when you look at the possible values, they are discrete or finite. The other kind of random variable is a continuous random variable whose possible values are determined through measuring. And since we measure the variable in order to determine the value, the value of the variable can be any number in one or more interval. So compared to discrete random variables, continuous random variables have infinite possible values, and they are not limited to integers or whole numbers. So examples include the height of a randomly selected student in one section, or the score in the exam of a randomly selected applicant of Ateneo. So again, those are considered as continuous random variables because the values are determined through an experiment, and they are determined, the values are obtained through measurement. Now, for inferential statistics, what we are interested in are continuous probability distributions. So inferential statistics comes from continuous probability distributions, where the curve f of x is the continuous probability distribution of a random variable x if the probability that x will be in a specified interval of numbers is the area under the curve f of x corresponding to the interval. And from elementary probability theory, you should know that continuous probability distributions are also known as probability curves or probability density functions or PDF. And continuous probability distributions have the following properties. First, f of x is greater than or equal to 0 for all values of x, and that the total area under the curve or under the continuous probability distribution f of x is equal to 1. And again, an essential point regarding continuous probability distributions is that the total area under continuous probability distribution is 1, 1 or 100%, and the area represents a probability. So in this slide, we can see an example of a probability curve f of x. That's the blue curve shown here. And the blue area under this curve, that's between values of x, a, and b, is the probability that x could take any value in the range a to b. So as mentioned earlier, this total area under the curve f of x is a probability, and that is the probability that x, or the random variable, will have a value that is between a and b. And that is mathematically denoted as the p, or the probability of x greater than or equal to a, but less than or equal to b. Because again, for continuous probability distributions, areas under that curve are probabilities. Now, mathematically speaking, this equation is just the same as this. This is the probability that x is greater than a, but less than b. And the value of this probability is just the same as this probability. Why? Whether we include a and b in the interval, the probability should be the same. Because if you, again, go back to our definition, x is a continuous random variable, which means that x has infinite possible values. So a is just one out of the infinite possible values for x. B is also just one of the infinite possible values for x. So the probability that x will be exactly equal to one specific value, given that there are infinite possible values, is almost 0. So it's not equal to 0, because if it's equal to 0, it means that it's impossible to happen. But we know that it's possible. It's just that the probability is very, very low, since this is one very specific value out of infinite possible values. So the probability that x will be equal to any specific value is almost 0. It's not 0, but it's almost 0. That's why whether we include a or b or not in the computation of the probability, the total area under the curve will be the same, and the probability should be the same. Now, one specific continuous probability distribution that we are interested in is the normal probability distribution, whose f of x is equal to this equation. That's 1 over sigma times the square root of 2 pi times e raised to -1/2 times the square of x minus mu over sigma, where mu is the mean of all values of x, sigma is the standard deviation of all values of x, and then we have constants pi and e. So this is the f of x. This is the PDF of the normal distribution, and we know that the normal distribution is characterized by a bell-shaped symmetrical curve, which means that if you graph this equation, we will have something that looks like that. And here are some of the properties of the normal distribution. First, the mean, median, and mode are equal to each other. And this is the only probability distribution with this property, where all the three measures of central tendency are equal. So the average of all values of x is the one at the center. The median, that's the literal center, where you have half of the numbers lower than that value and the other half are bigger than that value. That's also at the same point. And this is also the mode or the most frequent number in the entire data set. So again, all three measures of central tendency are equal for normal distributions. Next, the curve is symmetrical about its mean. So again, the mean is the one here at the center. And since the normal curve is symmetrical about the mean, the left and the right halves of the curve are mirror images. So this side is a mirror image of this side. And just like any other continuous probability distribution, the total area under the normal distribution is 1. So the total area under this curve is 100%. And since the mean cuts the normal distribution into equal halves, the total area to the left of the mean is the same as the total area to the right of the mean, which is 50%. Now, the tails of the normal distribution extend to infinity in both directions. So this tail extends to negative infinity, while this tail extends to positive infinity. And those tails get closer to the horizontal axis, but they never touch it. Because again, in a continuous random variable, there are infinite possible values. So that's also reflected in the normal distribution. That's why the tails extend to both directions. But even if the tails are asymptotic to the x-axis or to the horizontal axis, the total area under the curve will still be equal to 100%. Finally, there are an infinite number of normal curves depending on two parameters, the mean and the standard depth. So as long as a normal distribution has a unique set of mean and standard deviation, then if you compare that to a different normal distribution with a different set of parameters, then they will look differently. So that is shown here in this slide. So in the first set of normal curves, we can see two normal curves with similar shapes, but they just differ in terms of the center or their location along the x-axis. This curve is somewhere to the right of this other normal curve, and that is because they differ in terms of the mean. So remember, the mean is the one at the center, and since this curve is at the right compared to this one, this indicates that this mean is bigger compared to this mean. So this data set of normal random variables, has a bigger average compared to the other one. But since they have the same shape, that is an indication that they have the same standard deviation. Because remember, the standard deviation is a measure of variation. It's a measure of spread, how far apart the values are from each other. And since the standard deviation is the same, then we expect that their distribution should have the same shape. And that is shown here in the first set. Now, in the other set, we have two different curves that have the same center, but they have different shapes. One is a bit taller and thinner, while the other one is wider and flatter. Now, in terms of the mean, both normal distributions have the same mean. That's why they have the same center, they have the same location along the x-axis because they have the same value for the mean. But as we can see here, their shapes differ, and that is because they differ in terms of the standard deviation. So one standard deviation is bigger compared to the other, which explains the difference in the spread. And between these two, which one has a bigger standard deviation? As mentioned earlier, sigma or the standard deviation is a measure of spread, and a bigger standard deviation means that the values are more spread out or more varied from each other. Therefore, between these two, the one that has a bigger standard deviation is the flatter and wider one, because the values of x are more scattered, are more far apart compared to this curve with a smaller standard deviation. Now, since the normal probability distribution is one specific kind of a continuous probability distribution, then an area under the normal curve is also considered as a probability. So just like the example earlier, here if you have this normal curve and this shaded part as the area under the curve between values A and B, then we can denote this as a probability. And this is specifically the probability that a normal random variable x will have a value that is between this value and this value. So again, just like any continuous probability distribution, the total area under the curve of a normal probability distribution is also a probability. Now, from empirical rule, at least, there are three known proportions. From module 2, we talked about the empirical rule. According to the empirical rule, the interval that is one standard dev from the mean, one to the left and one to the right, contains 68.26% of all values of the variable. While the interval two standard deviations from the mean, so two standard deviations to the left, to two standard deviations to the right, this interval contains 95.44% of all values of x. And finally, for three standard deviations, that's 99.73%. Now, in Module 2, we talked about these as percentages for the total number of, total percentage of x that falls within their intervals. And as mentioned earlier, these are proportions, these are areas under the curve, which means that these are also probabilities. So 68.26% is also a probability. And this is the probability that a randomly selected value of x will fall between this point to this point. There's a 68.26% chance that a randomly selected normal random variable x will have a value that is within one standard deviation from the mean. And if you increase that interval to two standard deviations, the probability that x will be inside that interval is 95.44%. And then for three standard deviations, that's 99.73%. So at least we have three known percentages. And now we also know them to be probabilities as well. Now, mathematically speaking, how do we compute for those probabilities? So these are already known, but how do we compute for the others? From calculus, we know that to get the total area under the curve for a specified interval a to b, we get this area by getting the definite integral over a and b. So we know f of x that was shown earlier. So we will have to do a compute for the definite integral of f of x from a to b in order to get that total area. Now, a simpler way to get the probability without having to do definite integrals is through the standard normal distribution. And the standard normal distribution is basically a standardized normal distribution. So whatever the mean and the standard dev of a normal distribution is, that is standardized so that the mean will be equal to 0 and the standard deviation will be equal to 1. And whatever the normal distribution is, once it is standardized, once it is converted to the z or the standard normal distribution, then we can use a simpler way in order to get probabilities for any interval. So visually, this is again another way to show what happens when we standardize normal distributions. So again, if this is your normal random variable x, the value at the center is the mean. But when we standardize that, when we convert x to z or to the standard normal distribution, the center becomes 0. And this is originally one standard deviation to the left of the mean, and this is one standard deviation to the right of the mean. Again, that is standardized to 1. So this becomes -1, and this becomes 1. So again, whatever the normal distribution is, whatever the mean and the standard dev was, when that is standardized or converted to the standard normal distribution, the mean becomes 0 and the standard dev becomes 1. And we standardize x using this simple formula. That's x minus the mean of x, or the average of all values of x, over sigma, or the standard deviation of all values of x. So it is a lot simpler to just convert any normal distribution to z in order to get probabilities instead of having to compute for definite integrals for whatever the f of x or the PDF is of the normal distribution. Now, a commonly used tool to determine probabilities involving the standard normal distribution is called the standard normal table. And a standard normal table is a table that lists areas under the standard normal curve. But there are different ways how the standard normal table is constructed. Some standard normal tables give the area to the right of the mean up to a certain z value of interest. So the mean is at the center, that's 0. So some standard normal tables give the area between a z-score and the mean. Some standard normal tables, on the other hand, give the area to the right of a z-score, while some other standard normal tables give the area to the left of a z-score. So before interpreting, before using any standard normal table that you can find in a textbook or in the internet, you have to determine first how the table was constructed in order to know how to properly use it. Now, the one that we will be using for this course follows the third kind. Okay? The standard normal table that we will use provides areas to the left of a certain z-score. And in that table, the values of z are shown in the first column and in the first row. So accurate up to the nearest 10th for the first column and up to the nearest 100th in the first row. And in order to find the probabilities, we have to find intersections. The intersection of the first row and the first column, and the number at the intersection is the area to the left of that z-score. So for example, if we were asked to find the probability that a z-score is less than or equal to -1.15, or basically this is asking for the total area to the left of a z-score which is -1.15, we can do this, we can find this through the standard normal table. So this is the standard normal table that we will be using. As shown here at the top, the shaded area, the blue shaded part here is an area to the left of a z-score, because again, our table gives us areas to the left. So if we are looking for the area to the left of z-score -1.15, -1.15, we look for -1.1, the value up to the 10th digit in the first column, and we can find it here. And to find the exact probability to the, or the exact area to the left of -1.15, we will move to the right until we find the intersection with column header 0.05. Because again, the z-score that we are interested in is -1.15. And if we look for the value at the intersection, that is 0.1251. That is the area to the left of -1.15. So that's how we use the table to get the area to the left of z-score -1.15. Another example, we need to get the area to the left of positive 1.15. So again, in order to find this, we will use the same procedure. First, look for the values up to the 10th digit, and then find the intersection up to the 100th digit. So using the standard normal table again, now we will move to the second page with the positive z-scores. So as you can see here, this is positive. The z-score now goes beyond the center, which is 0, and it still gives us the area to the left. So again, we are looking for the area to the left of 1.15. So we find that here at 1.1 and at the intersection of 0.05. So that's 1.1 and 0.05. The value at the intersection is 0.8749, and that is the area to the left of z-score 1.15. Or this is the probability that the z-score will be less than or equal to 1.15. Now, in another example, we are asked to find the probability that z is between 0 and 1. Okay? Or visually, we need to look for the total area between the center, between 0 and a z-score, which is 1. Now, if you go back to the table, let's say this is 1. We know that if we look for 1 in the table will give us not the area between 0 and 1, but the total area to the left of 1. So if you search for that here in the table, that's 1.0 and 0.00, that's 0.8413. That's the total area to the left of positive 1. But the problem is asking for just this area. So if the area to the left of 1 is 0.8413, how do we get the area in between 0 and 1? We can do that by getting the area to the left of 0 and then subtracting that from the area to the left of 1. So when we get this subtracted by this area, we will be left with the area in between. So again, the area to the left of 1 is 0.8413. The area to the left of 0, remember this is the center, this is the mean. And as indicated here as well in the table, the total area to the left of 0 is 0.5. So if you get the difference between 0.8413 and 0.5, you will get the total area in between 0 and 1, which is 34.13%. So that's how we find probabilities between two values using our standard normal table. Another example is this. Find the probability that the z-score is between negative 2.53 to positive 2.53. So just like what we did earlier, we can first get the area to the left of 2.53 and then subtract the area to the left of negative 2.53 to find the area in between the two z-scores. So using the table, again, the area to the left of 2.53 is the intersection of 2.5 and 0.03, which is 0.9943. And then we will subtract from 0.9943 the area to the left of negative 2.53, which is this one, 0.0057. So that's 0.9943 minus 0.0057. You will get the area in between, which is 98.86%. So that's the probability that z will be between negative 2.53 and 2.53. Now, what if the probability that is being asked from us, or the area that we need to compute for, is an area to the right of a certain z-score? So in this case, we need to get the area to the right of z-score, which is negative 2, which is shown here visually. So this is negative 2 to the left of the center, and then we need to get the total area to its right. Now, if you look for negative 2 in our standard normal table, what our table will give us is this area instead, because our table always gives us the area to the left of a z-score. So if we search for negative 2 in our table, we will get 0.0228. And again, 0.0228, that is not this shaded area here, but that is this unshaded area, and that's 0.0228. And since we know that the total area under a normal probability curve is 1, and we need this area here, we can just subtract this area from 1 in order to get this probability. So if we subtract 0.0228 from 1, we will get the total area, which is 0.9772. So that's one way for us to get the area to the right of a certain z-score using our standard normal table. Now, another way to do this is to use the fact that the normal distribution is symmetrical, which means that the total area to the right of -2 must be the same as the total area to the left of +2, right? That's the mirror image. Area to the right of -2 should be the same as the area to the left of +2. So instead of doing this procedure of getting this and subtracting this from 1, you can look for the area to the left of the mirror image instead. So the total area to the left of 2. So if you search for 2 in the standard normal table, you will get 0.9772, which is again the same as what we would have obtained if we did the first procedure that we discussed earlier. So again, there are many possible ways to get probabilities or areas using the standard normal table. So just feel free to explore whatever will work best for you. Now, most calculators nowadays, especially the newer versions, also allow the computation of certain probabilities. So in most calculators with statistics functions, just look for the normal distribution or the DISTR function inside the stat mode. And when you access those functions, you will be able to choose between different functions inside. And some of the usual functions involving the standard normal distribution in calculators are P, Q, and R. Now, the P function in calculators that's used in order to find the area to the left. So that's basically looking for the area to the left of whatever z-score you input in the calculator. Q, on the other hand, refers to this kind, okay, this kind of standard normal table. So whatever z-score you input using the Q function, the calculator will give you the area between 0 and whatever that z-score is. And then the third one, the R function, gives you the area to the right of whatever z-score you input in your calculator. So visually, if this is the z-score that you input using your R function, the function will give you this total area. So these are some of the functions that you can find in calculators with the standard normal distribution functions. So using those functions for the previous examples that we used, that we've discussed, so if you need to look for the area to the left of -1.15, then you can just use the P function. So use P function and then type in the z-score -1.15, and the calculator will give you a more exact value, precise up to 5 decimal places, which is 0.12507, which is the same as what you would obtain if you use the standard normal table. Now for the second example, that's the area to the left of 1.15. Again, you can just use the P function and then input 1.15, and the calculator will give you 0.87493. Now for the third example, that's the area between 0 and 1. You can use the Q function because, again, the value here is 0. So you can use the Q function to find the area between 0 and the z-score 1. And when you use this function, you will get 0.3413. And finally, if you need to get the area to the right of any z-score, you can use the R function. So that's R, and then input the z-score that you need. And then the function will give you the total area to its right. And in this case, the calculator gives 0.97725 or 0.9772 if you use the standard normal table. So again, these options are available and you are free to use them if your calculator has those functions. Now, aside from finding probabilities, standard normal tables also allow us to do the opposite. Sometimes we are given a probability and we need to look for the corresponding z-score. So we can also do that using the standard normal table. And unfortunately, this is not something that is possible using most calculators. So calculators might be able to give you areas to the left or to the right or in between the mean, but it can't do the opposite. So for these kinds of problems where you need to find the z-score, you have to go back to the use of the standard normal table. So this notation here, that's positive, negative z with a subscript, which is a number. This is how we write z-scores. So the p here is a number. That subscript is an area. That's a probability. And the sign before the z tells us where that area is coming from. So if you have positive z, okay, sometimes if it's positive, then you don't see the positive sign is not written anymore. The subscript is an area that comes from the right, okay? Or that total area is the area to the right of that particular z-score. While if the z-score has a negative sign, that subscript is the area to the left of that z-score. So this is annotation, and if you see something like this indicates a z-score, okay? And the area or the probability is the value in the subscript. For example, if you are presented with this notation, that's z with a subscript 0.025, visually, that means that this z-score has an area to the right, which is equal to 0.025. Okay, so this is a z-score whose area to its right, or its right-hand tail area, is 0.025, which means that the total area to its left is just the complement. So that's 1 minus 0.025 or 0.975. So we need to look for this z-score, what the value of the z-score is, so that its area to the left is 0.975 and its total area to the right is 0.025. And we can find that using the standard normal table. So remember, our standard normal table gives areas to the left, and the area to the left of this z-score is 0.975. So we will look for 0.975 in the standard normal table to get the corresponding z-score. So again, we will look for 0.975 here, look for the value, and if you carefully go through the different values, you can actually find 0.975 inside the table, and that is at the intersection of 1.9 and 0.06, which means that the z-score that has an area of 97.5% to its left, or the z-score with an area of 2.5% to its right, is positive 1.96. So that's how we find 1.96 in the standard normal table. Now, technically speaking, every z-score can be denoted using a negative or a positive z-score. So this one is denoted as z sub 0.025 because 0.025 is an area to its right, but this can also be denoted as negative z sub 0.975 because 0.975 is the area to the left of that z-score. But the norm for z-scores is to use whatever notation will use a smaller value for the subscript. Usually, the subscript should be less than 50%. That's why between negative z sa 0.975 and z sa 0.025, this is the more commonly used way to denote 1.96. So we have here some other examples. So we have negative z sa 0.004 or a z-score with an area of 0.004 to its left. Technically, again, this is the same as a z-score whose area to its right is 0.996. But again, the norm is to represent it using this notation because the subscript here is less than 0.5. So like what we did earlier, just look for 0.004 in the table and you will find the value of z. So if you go back to the table and search for 0.004, we will also find an exact value equal to 0.004, and that's at the intersection of negative 2.6 and 0.05, which means that the z-score is equal to negative 2.65. Negative 2.65 has an area of 0.004 to its left and an area of 0.996 to its right. Now, in another example, that's positive z sa 0.03, which means that this z-score has an area of 3% to its right and an area of 97% to its left. And again, given that our table gives us areas to the left, we will look for 0.97 instead in the table. So looking for 0.97, we do not find a probability that's exactly equal to 0.97. We have here two close values, 0.9699 and 0.9706. And when this happens, our rule is to get the corresponding z-score of the probability closest to what we are looking for. So between the two, the closest to 0.97 is this, 0.9699. So the corresponding z-score must be 1.88. So the z-score that is denoted by z sa 0.03 or negative z sa 0.97 is 1.88. So again, that's our rule. If the exact p is not in the table, we get the corresponding z-score of the probability closest to what we are looking for. Now, in another example, we are looking for a z-score with an area to its left of 0.009 or a z-score with an area to its right of 0.991. So again, you will look for 0.009 in the table. And if you search for 0.009, we will not find an exact probability, which is 0.009. And if you look for the closest, again, there is no closest between the two options. 0.009 is exactly in between 0.0091 and 0.0089. When this happens, we will get the average of the z-scores for these two probabilities. So for 0.0091, that's negative 2.36. And then for 0.0089, that's negative 2.37. So get the average of negative 2.36 and negative 2.37. So the corresponding z-score must be negative 3.65. So that's our rule. If the probability that you're looking for is in between two probabilities, we get the average of the corresponding z-scores. Now, using a standard normal table, we can also find a tolerance interval. Now, first, what is a tolerance interval? A tolerance interval that is denoted by this equation, that's mu plus minus k times sigma. This is an interval that contains a certain percentage of values. So a tolerance interval is any interval that contains a specified percentage of values. So in this example, we are being asked to find a tolerance interval that contains 99%, the middle 99% of measurements in a normal distribution. So visually, the middle 99% is shown here. The one at the center is the mean. This is the lower bound. This is the upper bound. This total area is 99%. And since the total area under the curve is 1 or 100%, it means that the total area for the two remaining sides is 1%. And if you divide that into 2, because the normal distribution is symmetric with respect to the mean, this area must be 0.005, and this area must also be 0.005. So since we have this area here to the left of this z-score, we can easily find this using the standard normal table. So again, look for 0.005. And if you search for 0.005, again, we do not find the exact value, and it's in between two z-score, two probabilities, 0.0051 and 0.0049. So like what was discussed earlier, when this happens, we get the average. That's negative 2.57 and negative 2.58. So the z-score must be negative 2.575. So this value is negative 2.575 to the left of the mean, and this is 2.575 to the right of the mean. So what is the tolerance interval that contains the middle 99%? That's mu plus minus 2.575 times sigma. Whatever the mean and the standard dev is of any normal distribution, if you plug in 2.575 to that equation, you will be able to get this lower limit and upper limit such that the total percentage of values within that interval is 99% of the entire population. So that's how we compute, or how we find, or how we construct tolerance intervals. Now we can also try to look for tolerance intervals for involving other percentages. So we can try 95%. So here, instead of 99%, if the middle percentage is 95%, it means that the total area for the two other sides must be 5%. And if you split that into 2, this should be 0.025, and this is 0.025 as well. So like what we did earlier, look for 0.025 in the standard normal table. And here, luckily, 0.025 is exactly in the table. So we will just get the corresponding z-score, which is negative 1.96. So for 95%, the z-score here is negative 1.96. The z-score here must be positive 1.96. So the tolerance interval that contains 99% is mu plus minus 1.96 times sigma. And then for another example, let's use 0.9973. So if it's 0.9973 here at the center, it means that we have 0.0027 as the total area for the two other sides. And if you divide that into 2, this area must be 0.00135, and this is also 0.00135. So if you search for 0.00135, we find the exact value here, and that is for negative 3.00. And again, this should not be a surprise, because if you go back to the empirical rule, the interval 3 standard deviations from the mean contains 99.73%. Okay, so now using the concept of tolerance intervals, we are no longer just limited to the percentages mentioned in the empirical rule, because it's now possible for us to also look for intervals that contain other percentages, like 95% as shown in this example.